Hello, everyone. Today, we are going to discuss Semester 7 Mechanical Engineering, Advanced Manufacturing Technology. Thank you, Professor Ananya.
This subject is the backbone of mechanical engineering and helps students connect theory with real-world manufacturing technology.
Hey everyone, and welcome. Today we're getting into something really cool in advanced manufacturing, the art of shaping things without even touching them. Chalo, let's dive right in. So, let me ask you something. How would you carve a jet engine blade, from a metal that's way tougher than steel, but without touching it? Sounds impossible, right? I mean, your normal tools would just give up. They'd break, they'd melt. The solution isn't about more power. It's about a totally different, a much smarter way of thinking.
Okay, so let's break it down. Think of traditional machining like using a hammer and chisel. It's all about physical force. You get a lot of heat, a lot of stress on the material, and your chisel, well, it gets dull. But advanced machining, that's a whole different game. It's more like using a laser or a chemical. It's energy-based. So the process is cool, there's no stress, and best of all, the tool doesn't wear down. That's how you shape the impossible.
All right, first up, let's talk about something that sounds straight out of a sci-fi movie, electrochemical machining, or ECM. Now, the best way to get this is to think of something you probably already know, electroplating. ECM is basically that, but flipped completely backwards. You know how electroplating adds a shiny metal coating to something? Well, ECM does the total opposite. It uses electricity and a simple saltwater solution to remove metal, and we're talking super precise, atom by atom. It's like having microscopic hands that just pluck away the atoms you don't want. Controlled erosion. It's as cool as it sounds.
So how does this magic actually work? It's a pretty neat four-step process. First, the setup. You take your workpiece, that's the positive anode, and your tool, the negative cathode, and you put them in a bath of electrolyte, which is basically conductive salt water. Step 2, you pump that electrolyte at high pressure into the tiny gap between the part and the tool. Step 3, switch on the juice, a low-voltage, high-current supply. And finally, step 4, the reaction kicks off. Metal ions start dissolving from the workpiece, and it slowly takes the shape of the tool, like magic.
Okay, for all you engineering folks out there, here's the main funda you need to remember for the removal rate. It's super simple. Closer the gap, faster the cut. That's it. The material removal rate is inversely proportional to that gap. So the smaller the gap, the quicker the material comes off. That's the secret sauce to controlling this whole thing.
So like everything in engineering, right, there are trade-offs. The advantages are huge. There's no tool wear at all, and you can machine really complex shapes in the toughest metals without any heat or stress. Amazing for something like a turbine blade. But the disadvantages are real too. It uses a lot of electricity, the equipment is expensive, and that saltwater electrolyte is corrosive. So it's a fantastic tool, but you have to pick the right job for it.
Okay, quick memory check. In ECM, which part is the workpiece that's getting shaped? Is it the anode or the cathode? It's the anode, the positive one. Got it? Good.
All right, let's move on. What happens when you take the cool science of ECM and you mix it with a good old grinding wheel? Well, you get something called electrochemical grinding, or ECG. Think of it as grinding's much, much smarter cousin.
So what's the big difference? Well, ECM, as we saw, is 100% electrochemical. There's no contact. But ECG, it's a hybrid. About 90% of the work is still done by that same electrochemical process, dissolving the metal. The other 10%, that's the grinding wheel, but it's not really grinding. It's more like a janitor, just lightly sweeping away the dissolved stuff. So the heavy lifting is done by chemistry, not the wheel.
And think about this. Because that wheel is barely working, doing only 10% of the job, it lasts for ages. We're talking more than 10 times longer than a normal grinding wheel. This is perfect for stuff that needs to be super sharp and totally burr-free. A classic example? Mass-producing hypodermic needles. ECG is perfect for that. Okay, let's lock this in. What's the main difference in how material gets removed between ECM and ECG? Right, ECG is a hybrid, 90% electrochemical, 10% mechanical. Okay, time to switch gears completely. We're moving away from electricity and diving into pure chemistry. Let's talk about chemical machining. You could say it's literally an acid test for metals. The basic idea is incredibly simple. Protect the bits you want to keep and let a chemical eat away everything else.
The best way to picture this is like making a rangoli with a stencil. You put the stencil down to protect the floor, and the color only goes in the open spots, right? Chemical machining is exactly the same idea. You apply a protective layer, which we call a masking. That's your stencil. Then you use a chemical called an etchant, and it carves away only the metal that's not protected. Simple as that.
And the process itself is super straightforward. Step 1, you've got to clean the part really, really well. Step 2, you mask it, applying that protective layer all over. Step 3, you scribe it, which just means you cut your design into the masking, exposing the metal underneath. Step 4, the fun part, you etch it. Just dip the whole thing in a chemical bath. And finally, step 5, you demask it, peeling off the protective layer to see your finished part. So that's clean, mask, scribe, etch, and demask.
So, when would you use this? Well, it's perfect for making large, thin, and fragile parts lighter. Think about the skin of an airplane. You can't just press down on it with a tool. But with CHM, you can remove material without any stress. The downsides? It's kind of slow, and you have to be careful about the chemical eating sideways under the mask. That's called undercutting, which can mess with your precision.
Time for one last check-in on this topic. In chemical machining, what do we call that protective layer that acts like a stencil? It's called the maskant. Got it.
So there you have it, 3 powerful ways to machine without touching. Look, as engineers, it's not enough to just know these things exist. You have to think of them as a toolkit. And the most important skill is knowing which tool to pull out for which job.
So let's put it all together in a quick summary. For complex 3D shapes and super hard metals, you want ECM. But remember, it's thirsty for power. Need a perfect, burr-free ground finish? ECG is your hero. And for making large, thin sheets lighter, that's a job for CHM. Just be patient with it. Each one has its superpower.
So, why is all this so important? Because the future of making things isn't just about pushing harder or cutting faster. It's about cutting smarter. It's about precision. It's about working without brute force. This is a mindset shift. And honestly, understanding this way of thinking is what's going to help you innovate, whether you end up designing tiny microchips or building rockets to explore space.
And really, it all boils down to one fundamental lesson, doesn't it? Sometimes the most powerful way to shape something is to not touch it at all. It's about moving beyond just physical force and gaining control right down at the atomic level.
Which leaves me with one final thought for you. As we engineer the future, from the smallest microchips to rovers on Mars, which of these no-touch techniques do you think will become the most important tool in our arsenal? The answer to that, well, that's for you and your generation of engineers to decide. Thanks for joining me.